Hi, I'm Tim. Today I'm going to give you a talk, mostly like a walk in the history of computers and LLMs, more like a position paper. But yeah, let's have a look. So what is so special about LLMs? One thing people argue, it's scaling laws. If you scale up the model architecture, the amount of training and the compute, it performs better in the language modeling task. Of course, you have more compute, more data, larger model, it performs better. What's actually special is we trained on the language modeling task. It's a specific task, nothing else. But it turns out to be able to solve other kind of tasks in zero shot. For example, translation, summarization, question answering. You don't train LLMs for those tasks, but it does work after you train it for the language modeling task in a large amount. This is not something you can predict from a smaller scale model. And people call this emergent behavior. Definitely, it's not something unique in LLMs. For example, it's been discussed in physics and biology kind of 50 years ago. Like this paper by Anderson, who's a Nobel Prize winner, have like this titled it as more is different. For example, the behavior of large and complex aggregate of elementary particle turns out basically have some property that you can't predict from the behavior of the particle themselves individually. He already called it a kind of emergent behavior at the time. And this kind of emergence is also not unique for physics and biology. It's been there in machine learning a long time ago as well. This idea, 1982, from Hopfield, the Nobel Prize winner, together with Hinton last year. This paper, it's this idea of Hopfield networks. Basically, early idea of neural networks in the sense that you have lots of neurons and then you connect them together, you train them for a task, and then it shows you some behavior that you can't understand simply from the behavior of a single perceptron. And in the title, it's emergent collective computational abilities. The term, it's been there for a while now. And if you think about modern computer, it's also the case. Also emergence, right? Like you build computer with this simple logic gate that only do one specific task, right? You put lots of them together and then it's able to run video game, add an image. The logic gate, the fundamental component, it's not trained for this task, but somehow it becomes zero-shot solver for tasks other than just doing logic operation. Let's talk about that in more detail, right? Computer, how is that emergent? How is that similar to LLMs? If you look at this idea of zero-shot solver back to 80 years ago from Alan Turing, it's in its paper for Turing machine. It's already mentioned, right? This session title is called a universal computing machine. The idea of universal Turing machine. You can think of this universality a different way of saying zero shot, right? Concretely, after Turing proposed this idea, people tried to build computers. At the beginning, it's very specialized. So you build a specific machine to solve a specific task. For example, this code cracker in the movie Turing helped build one machine for one task at the time, like that. Expensive, you can't build a machine for every task. Early computer scientists try to realize this universal Turing machine, this idea, like how do we get that? The next iteration, people create this hardwire programmable computer. Some people call it the first computer. But basically what it is instead of building a specific machine for a specific task, they build a machine that have loads of logic operations. And then if you want to solve a new task, you just wire them up differently. A collection of different units and switches, that's what it is. And then at the time, reprogram the machine implies manual rewiring of the switches. Still not very practical. Still part of the hardware at this time program. That's different from data, right? Data is 0 and 1 signal. And then push this even further, the real kind of the modern definition of computer is this store program computer that's defined by von Neumann. This idea of von Neumann architecture is to represent program as the same type as data. So instead of a wiring setup, your program is 0 and 1s, just like the data. By pumping this 0 and 1s through the computer, it activates different switches and then indicate what to do with the 0 and 1s that's in your data. This basically allows computer to read and solve arbitrary programs for which they were not set up by wiring. They're wired in a specific way, and this is a very general wiring. And that kind of achieves zero shot. Similarly, like LLMs, the simplest component of our phrasing of language modeling is this factorization of condition probability, like given some prefix tokens and predict the next one. This is like the unit of computing, the logic gate of LLMs, like the simplest task you can factorize into. And then similar pattern of development, like early stage of NLP, you also trained one single model for a specific NLP task, right? Like question answering, translation, but they're all separate models. And then later on, people have similar ideas. Can we have the single model do all sorts of tasks instead of training one for a new one? So early idea people tried out, for example, like this, is to kind of have a special tag in the neural network. So basically another condition, some flags. For example, 0 means translation task, 1 means question answering task, and then you train them on multiple tasks, multiple data sets. This is very much like this switches, right? Like you have a different flag for different tasks. So you have to kind of rewiring them in a sense. And then people try to push it further. Instead of representing this task identification into some kind of flags, now people try to have them in the same format as the input. So put them in text as well. For example, this work have a prefix of the input, like saying, oh, translation, and then some Chinese sentence, and it will output English, right? Or have a words like question answering, and then you throw the question, but all of them are in text or in the same representation. So that's like the next step forward. But you can already see this is very much like a von Neumann machine, right? The data and task are in the same representation. This already looks very similar to language modeling. So to generalize that further, in this paper, GPT-2, they say, sure, why not just language modeling, that single task, and then see whether it works. They try them out, and it works. That's what makes people surprised. But you can see the same path. It's similar, very similar to the history of computer. To connect the dots, computers takes in program and data and give you the answer. LLMs taking also your prompt and give you the answer, right? And they're also similar in the way that the level of abstraction, you can kind of find the corresponding part. They both have some basic compute architecture. In computer, you have gates, some CPUs that calculate something native. That's basically some representation that's native to the computation. And similar to LLMs, you have something handle vectors. And then above that, you have things that translate your problem into this kind of computing medium. So in that way, they are also similar. And then this is like the development, the history I just mentioned. Special purpose slowly move towards general purpose. Both of them have the similar path. So the fundamental difference, unlike the similarity, LLMs are more accessible but expensive due to the informal reasoning, right? So we often think about computer, some problem in terms of complexity theory, how complex is a problem, but when you think about it, they are all discussed in the condition that the problem already been formalized, right? If you already write it down in the program, then you can analyze the complexity of that. But the expensive part is actually how to translate your problem in the informal setup into the formalized program. So that's like what a programmer is doing. It's a task. People don't think about the complexity that much. Of course, it comes with ambiguity and difficult to describe the problem precisely. Computer, it's lived in the world that's formally structured, logical, well-defined. So if you give a program, it will execute for sure without problem. But of course, if you want to use it, you have to learn the formal language. So that's the downside. And basically, this comparisons, we can see some findings. The zero-shot problem solving ability emerges when we combine a powerful compute architecture with suitable problem translator. If you think about computation ability, it's not a real property as we might think. For example, if you can phrase a problem into a surface and your initialization as a ball on the surface, and the goal is the kind of the minimum of the surface, and then throwing the ball on the surface and then let roll. When it stopped, it gives you the answer, right? This in itself, it's also doing computing. But the problem with that is it's hard to phrase the problem you want to solve into this kind of computing medium. You have to rely on something that can be translated well. That's a finding. And then another one is minimizing the gap between the language model of an LLM and the language model of the user. It's at the core of unlocking the full problem-solving ability of LLMs. So if you think of the distribution, your internal language model, in the natural language space, it's more spread out because there are different ways, like we understand concept differently. And then this mismatch, this misalignment, make it hard to communicate with the LLMs, right? You say something you want, and then it doesn't solve it for you. That's due to the misalignment between the two language models, you and the LLM. But in formal language, when you define the problem well, you know the computer has to solve it properly. In that sense, you kind of align yourself to the computer. You can see that the majority of the work in LLMs based on this. For example, you try to align yourself to the LLMs. This involves works like let's think step by step, this kind of prompting strategy. So you figured out some certain prompt that will allows the LLM to do what you want, right? Lots of works are going into that direction. And there are also another direction. You try to align the LLM to the user better, right? Like fine tuning, for example, for a specific task. That's like trying to move the distribution for the LLM towards you, align the other way around. And of course, there's something in between. But anyway, that's kind of, the pattern. So after all of that, the next question we want to think about is the future of computing. What kind of problem we want, like what do you want to compute? Like what's the ultimate goal of computer science? Humans want to delegate problem to some machine that can automatically solve it for you. And very often this thing happens in natural language. Like when I ask, for example, Johannes to help me with something, I don't want to write a program and then send it to Johannes and then, right? That takes a lot of time. The most natural form of problem solving, or we can call it reasoning, it's happening in natural language. And with the help of LLMs, maybe that's the future. And that's like the looking forward. And that's it. And we got this article in this Harvard Data Science Review. There are another session more about the outlook, like the future might look like. Some opinion of that in the paper that I didn't discuss today, but you are welcome to have a look.